Today's presentation will be about modeling data, and we'll be using rate of change to determine the best model. Quite often you'll come across graphs such as these in newspapers and or in magazines, and you'll be asked to look and interpret the data that you see. So just as a reminder about the average rate of change, we also refer to this as the slope, and we have looked at the slope of linear functions. And the slope is the ratio of the change in the vertical value to the change in the horizontal value. So we often say that slope is rise over run, where rise is the change in the vertical value and run is the change in the horizontal value. We also can refer to this as delta y, triangle meaning change, over delta x. And you'll recall that we did use a specific formula for slope, and we said to find the slope of a line between 2 points, you subtract the y's and you make that the numerator of the ratio, where you subtract the x's in the denominator. Now all of this means the same thing. The change in the vertical value is your rise, or your change in your y, and you get that by subtracting the y values, and then the change in the horizontal value will be the change in your x values, and you get that by subtracting your x values. So we'll use the average rate of change and sort of an analysis of the average rate of change to help us look at models and determine what model might be the best for a set of given data. So let's take a look at an example that you may have seen previously on producing t-shirts. Here we have a graph that shows the cost to produce t-shirts, where along the x or input axis we have the number of shirts produced, and in the vertical direction we have the cost to produce those shirts. And we're given 4 specific data points: 50, 1200 is my first ordered pair, 50 is the x, 1200 is the y, 100, 1600. Now, it is true that this is given as a bar graph instead of as ordered pairs, but we could also think of these as ordered pairs: input, output, 150 and 2000. And then our fourth ordered pair is 200, and 2400 is my output. And so the first thing we want to do is we want to look at what the slope of this particular graph would be. And in this case, we happen to have an exact linear function or a linear equation. If I were to plot these as points instead of as bars, I could connect these with a perfectly straight line. And that's not always the case, but in this case it happens to be true. And you can tell that by looking at the slope or rate of change. So we can look at the change in the y's and the change in the x's and see that it's going to be a constant. So looking at the first change in y, you can see we went from 1200 up to 1600. That's up by 400. Then we went from 1600 to 2000, again up by 400. And then lastly we went from 2000 to 2400, and that's up by 400. So the change in your y's is a positive 400. It's going up by 400. So we have a rise here. As we move from left to right, we can actually see that when we look at the graph. Now, if we look at our change in x, we go from 50 to 100. That's up by 50. We go from 100 to 150, again up by 50. And then 150 to 200 is also up by 50. So we have an increase in our run, that is our horizontal value of 50. And of course, when we have a positive divided by a positive, we have a positive, and we can write this 8 over 1 or just plain 8. Now, we'd like to write it 8 over 1 when we're talking about rise over run. And in fact, we could interpret this because remember, on our y-axis, we have cost, which is dollars, and on our x-axis, we have shirts. So what we're saying is that it costs $8 to produce every shirt, $8 per shirt. Our rise is our cost, our run is our number of shirts. So for every shirt, we have to pay $8. And in this case, we can see that we have what is called a constant rate of change. A constant rate of change. And when your rate of change is constant, you will have a linear function. And so we can look at the data, and when we see that the rate of change is constant, or in the case of not exactly constant, but very close to being constant, we know that a linear model will be a good model for this data. So let's look at a few other linear examples. Keeping in mind that when you have a constant rate of change, you might have a function that is increasing, or a function that is decreasing, or you might have a horizontal line. That would also be a function. That is, there's no change in the rise at all. Now, if we have a vertical line, it's not a function. So we're not going to be looking at vertical lines when we're talking about linear functions. We're going to be restricted to the three I just described. Positive slope, which is uphill from left to right. Negative slope, which is downhill from left to right. Or horizontal line, which is a zero slope, which is completely flat line with no rise whatsoever. So let's just take a look at a few examples. I'll pick some data points here. So for my x, I'm picking -2, 0, 2, 4, and 6. And for my y values, I'm going to pick 4, 6, 8, 10, and 12. Once again, we can look at our rise and our run, and in this case, we can see our rise is going to be up by 2 each time. So we've got a rise of 2. And if we look at what's happening in the x's, you'll notice these are also all going up by 2. So that's a run of 2. So that's a slope of 1. 2 divided by 2 can reduce to the value 1. Now, if we were to plot these points, and I'm going to use a scale here of 2. So 2, 4, 6, 8, 10 is my x scale. And then 2, 4, 6, 8, 10 also on my y-axis. And if we were to plot these points, we're going to see that they'll line up on a perfectly straight line because of this constant rate of change. So let's see, 0, 6, 2, 8, 4, 10, 6, 12, and then that first one was -2, 4 here. And again, you can see that what you have here is a perfectly straight line, and that perfectly straight line goes through these points. Linear function. It turns out it doesn't really matter which set of ordered pairs you use. So for example, I'm just going to pick these 2 points, 2, 8, and 6, 12. So 2, 8, and 612. And if I were to do the slope or look at the change in the rise and the run here, I would actually get up by 4 over 4, which also reduces to a slope of 1. So it doesn't matter which two pairs of points you use when you're doing a linear function, because the rate of change is a constant rate, and you will always get the same rate of change if you're looking at an exact linear function. Now, this happens to be an increasing function, because as we move along the line from left to right, that line is rising, and that's something that we've seen before. But linear functions don't always have to increase. They may have a negative slope. So let's look at another example. Negative 5, 0, 5, 10, and 15. For y's, 10, 8, 6, 4, and 2. So here are my x values and my y values. I'm going to set my scale just based on what I see here along the x-axis to be 5. So 5, 10, 15, 20, 25. And along the y-axis, I am going to go by 2, 4, 6, 8, and 10. And I'm just setting it this way strictly based on what I see in my table. And now I'm going to plot my points. Negative 5, 10 would be, according to my scale, 1 unit to the left and up to the 10. 0, 8, 5, 6, 10, 4, and 15, 2. Once again, we see that we have a straight line here through these points. And in this case, our slope is a negative, and we're going downhill from left to right. What is our slope? Well, let's look at our change. You will notice that the y's are dropping by 2, but the x's are increasing by 5. So our delta y over delta x would be down 2 to the right 5, because the y's are dropping by 2 and the x's are moving to the right. Left, remember, we're always going left to right. And the x's are increasing by 5 as we move from left to right. That is a decreasing linear function. Now, once again, the reason it's a linear function is that regardless of the points that I choose, the rate of change or the slope will be the same. Now, there's one other kind of linear function besides the ones with the positive slope and the negative slope. There's one other type, and that is what we call a constant function. Now, remember that when we're talking about rate of change, we're talking about the slope, and in a line or linear function, that slope is going to be the same no matter which two pair points that you select. But there's also what's called a constant function. And in the case of a constant function, you're going to see something like this. And I think you'll see why this is called a constant function, because remember that function machine that we talked about when we first talked about functions. You've got something going in, something going out. We call this our x, or our input. We call this our y, or our output. And look, what's the rule in here? Whenever a value from the x column goes in, the y value always comes out to be the same number. And when something is not changing, we call that a constant. So if you were to actually do the arithmetic and say, well, what happened to the y's? Well, Absolutely nothing. 0. It went up by none. But the x's are going up by 2. Well, regardless of what the x's go up by, the slope in this guy, rise over run, is going to be 0. And when you plot those points, put my scale here, 1, 2, 3 on the y-axis, go by 2's on the x-axis. You plot these points, negative 4, 3, negative 2, 3, 0, 3, 2, 3, and 4, 3. When you plot the points, look what you get. You get a horizontal line. Perfectly straight line, perfectly flat, no rise in the line. This is called a horizontal line, and it's also a constant function. And there are a lot of functions out there in the real world that are constant functions. One example I can think of is in Atlanta we have a train system called MARTA, and regardless of how many miles you ride that train, MARTA has one fixed price. So if the input is the number of miles you ride along the train, it doesn't matter. The output is going to be the same amount for every rider, regardless of how many miles they ride. So here's an application of a linear function, and this is to show you that in the real world, things are not always exactly linear, but you have situations where things are nearly linear. So we've got Tessa taking a math test here, and she's going to take 4 tests total. So along my x-axis, we have the tests that Tessa took. And those are tests 1, 2, 3, and 4. And along my y-axis, we have Tessa's scores. And let's see, from 68 to 84, I'm going to make a scale of 20 here, so I can get them all to fit in. And on her first test, she made 68. Now 70 would be halfway in between, so 68 would be somewhere down here. Then she made 75. It's about halfway between 70 and 80. And then she made 84 on test number 3. And then we are not sure what she made on test 4. Now we do know the first 3, 68, 75, 84. So we can complete those in our table. But our question is, if the trend continues, let's predict Tessa's score on her 4th test. Now if we were to look at our rate of change here, the change in the x is a constant value, you can see. Each one of these is going up by 1. So first test, second test, third test, fourth test, that's just 1. But the change in the y's are slightly different. She first goes up by 7 points, and then she goes up by 9 points. So she doesn't go up by exactly the same amount each time, but it's pretty close. 7 points and 9 points are pretty close. So we could, probably just generally predict if she keeps doing as well as this table is predicting, she's going to go up 7, 8, 9 points probably for the next one. So we might say, Tessa's going to score anywhere between 7, 8, or 9 points higher. So somewhere like maybe a 91 or a 92 or a 93. That would be along what we call the trend line for this data. That would put her somewhere for test 4 in the 90s. Well, we can use our calculator to make a model for this test and use it to see how well our model works. So I'm going to switch over here to the calculator. And in my calculator, I'm going to enter my data points, and I'm going to actually have the calculator do an official calculation of what we would call linear regression or trend line, and predict what the model would look like and see what the model would predict for her next test. So in order to do this, I am going to enter the data points into the calculator by pressing Stat 1 and then just entering my X's. 1, 2, 3, and 4. And in the second column, I'm going to enter my Y values, 68, 75, and 84. 68, 75, and 84. And actually, since I don't have the value for the fourth test, I need to leave that one blank. Now, what we're interested in finding is this last ordered pair. Now, there are a few keys to press here to get the calculator to find this best fit line, it's called. And those keys we press are Stat. Then I go over to Calc. So I use my arrow key here to move over to Calc. And I want to find the line, which is number 4, linear regression. And here's what the linear regression says. So it says that the line of best fit for Tessa's test taking is y equals ax plus b, very similar to y equals mx plus b. And it's A is 8, and remember we predicted about 8, a change of about 8, and her B is 59.666, and I'm going to change that to 60. I'm just going to round to 60. So y equals 8x plus 60 is the function that will predict how Tessa is going to do on test number 4. Now look at what this is saying. Rate of change or slope is 8. Y-intercept is 60, meaning that basically start at 60 and for each test go up about 8 points. So if we want to find test 4 and use our model, we would substitute our 4 for x, do the arithmetic, and we get 32. That's 4 tests, 8 points, going up 8 points each test. And we get that she's predicted to make about a 92. And we predicted that without actually finding the equation. But it's also important that you can recognize when you see a calculator screen. You can recognize what the calculator screen is telling you. Whether you're asked to actually do this kind of calculation or not, you should be able to read these calculator screens. And in the case of linear regression, and regression is just a word we use for finding the best fit model. And in the case of linear, you've got these two parameters, A and B. We would usually call our slope M, but the calculator calls it A. And you can see that because it's A times X, and that's where the slope would go. It's the number times X plus B. And in the case of this particular situation, Y would be 8X plus 60. Once you know that formula or model, we can use the model to see how good the model actually is, and we can also use it to predict future values. If I wanted to see how good this model is, I might test a couple of the points, see what happens. It won't be exact unless your rate of change is a constant. And we can see here our rate of change is not exactly a constant. So we won't get the exact value, but we'll get a pretty good predictor. So if I were to look at the second point, for example, 8 times 2 plus 60 is actually going to give me 76 and not 75, but that's pretty close. And in the case of a model, close is typically going to be good enough.